Okay, Jose Solis-Ocampo, Lab 2, Projectile Motion. So, for introduction, the purpose of this lab is to observe the motion of an object moving in a parabolic trajectory and compare the observed motion observed position to the two predicted positions from a computational model, one with the drag force while the other doesn't have a drag force. And the goal of this experiment is to demonstrate the principles of Newton's second law and see the effects of drag force with computational models. For fundamental principles used, first we have Newton's first law, which is an object at rest stays at rest, and an object in motion stays in motion, in constant motion, unless an external force is applied. Newton's second law is that the net force is changing based on object's velocity, and F equals ma. So force equals mass times acceleration. And also we have to know about air drag, which makes a projectile slow down, and especially in the x direction. Gravitation force, the attractive force between the earth and the object that pulls down, is negative mg in the y, and drag force, the resistive force that opposes the motion of an object, and terminal velocity when the gravitational force balances out with F drag. So here's some of the equations we use. The V average formula to see the average velocity of our object, the velocity update formula to update our object throughout the code, and the position update formula to also update the position, and Newton's second law F net equals ma to see all the forces acting on our object. Apart from this, we also use that the F drag, the drag force, is negative V times the absolute value of V squared times V hat, which shows the F drag and the drag force on the object in its trajectory. And we can also see that F net equals F gravity plus F drag. Here are some brief tracker results, and as we threw the object, we saw that the x position increased and the y decreased, showing that we did indeed have a parabolic trajectory, and that as time increased, our y decreased. Here's experimental overview. Our watered ball was in his hand at about this length and was thrown in this trajectory into the trash can, and this was 0. Here was our calibration and our calibration stick. The object was a paper ball. The surroundings were air resistance, drag force, gravity, and the initial push given. The experiment tracking was tracker, and the computational model was glow script. Initial conditions. The bottle's initial position and velocity were measured at the start of the object's motion at t equals 0. The object started at approximately that meters, and the initial velocity was estimated from the change in position over the time using the tracker data, giving an approximate initial value of 4.2 meters per second. And here's how I did that from these two values over here. And here's the glow script code. So for all the glow scripts, for all 3 of them, follow this code with this, following the Fnet and the drag force for the projectile motion. And here is our first results. The blue line shows the experiment, and the orange line shows the computational model. And this shows that since we didn't have a drag force in our computational model, well, the object was going to have a larger x value since there wasn't anything holding it back. And for the next thing, for the drag force, it was almost the same, except for then I added a b of 0.045, which is about the mass of the object. And I continued with adding the same glow script code as before. And we see here, adding that computational model with the drag and gravity, we saw that our object reached a much less x position, showing that the drag decreased our position drastically. So this is error, incorrect initial position or velocity value, uncalculated outside forces like wind in the room, not calibrated correctly, the ball shape, and issues in the computational model. So does any of this show terminal velocity? Well, this one is the model without drag, and this one's with drag. So the one without drag doesn't, but the one with drag does, since we can see that the velocity starts flattening out, and terminal velocity is shown when the slope of the velocity is 0, since the velocity isn't changing as much since it reached its terminal velocity, and mg equals drag. So how would time change if the object was thrown straight up? So since if the object was thrown straight up, the time would be longer, and the time to peak for the object to peak is longer, meaning it stays in the air longer and generates more, which mean it had more force in it. And since it had more force, it has more velocity and needs more time for it to reach 0 from greater force. And since up and down has the sine component, we see here that the sine component would activate here, and since if it was the angle was lower than 0, that means that the experiment would be lower and causing our time to be longer.